Hey everyone, good afternoon. I think we have enough people to start. Thank you so much for joining. My name is Ahmad Bukhari. I'm faculty at CCPS St. John University. I'm honored to introduce to our today's speaker, Dr. Naveed Afzal. Dr. Afzal is a lead data scientist at Humana. Dr. Naveed did his PhD in natural language processing from University of Wolverhampton, UK, and the master degree in advanced software engineering from University of Sheffield, also from United Kingdom. He's the author of several books and academic publications, and has served in past at several academic positions as well. He was an assistant professor at King Abdulaziz University, Saudi Arabia. Then he was a researcher, research fellow at Mayo Clinic, Rochester, and he extensively his work mainly on the unstructured data using various NLP, machine learning, and deep learning approaches to build supervised and unsupervised models that have been produced meaningful insights to facilitate the decision-making process for various business use cases. We are very excited and we welcome to our speaker. Thank you so much, Dr. Afzal, for sparing time. Over to you. Please share your screen and yeah, we can see your face and we can also see your slides.
Thank you very much for the kind introduction and the opportunity. So today I'm going to talk about unstructured data. We hear a lot about people saying data is like a fuel, data is very vital. So we'll talk about but not all the data is useful. For a specific use case, you are looking for a specific data set. So as an AI professional, we'll talk about what different types of data. Here I have mentioned unstructured data, what is structured data, what is unstructured data, why natural language processing, and then finally we will also talk about why healthcare. There are so many other domains, but why unstructured data, natural language processing, and healthcare are closely related. So in this talk, we'll briefly talk about what is the healthcare in USA in terms of what the trends are and how much USA spends per capita as compared to its other developed countries, especially. And then we'll briefly talk about NLP, what NLP is, how NLP is being done, what are various stages involved, and then various stages of NLP. And after that, I will talk about a clinical use case, which I worked previously at Mayo Clinic. That is real time is being currently used at Mayo Clinic for that specific disease detection. And we will talk about a little bit about that and how it was developed, and also how it is being used currently. So let's, if you have any questions, I think we can take it at the end.
Yes.
Ahmad, what you want?
What we do there. So as soon you finished your webinar, so we usually ask to the participant to write questions in the chat. But if we have enough time, we also allow to the participant to open their mic and even video to directly to communicate with you. If time is short, we usually take the questions and then pick some questions to for the speakers to answer. Thank you.
I think I will try to get some time spare at the end to have the questions ready. So let's look at this. Is the if you look at per capita in dollars which US spends and comparison to the developed countries, if you see there is more money is being spent in US per capita as compared to all the other developed countries. So there is a huge money which is being spent, but the outcomes are, in terms of outcome, US outcome is not better even compared to what you say in healthcare in terms of Scandinavian countries, even though US spend more money. And if you see this gap is widening up and up as we move along. So the US is spending more money, or in other words, if you want to describe it, we are getting less value out of the money we spent in specifically in healthcare. And if you look at these different distinctions in terms of hospital care, physical and clinical services, prescription drugs, and administration, so you see the whole breakdown of the cost is going up and up and up as we move along the years. So why it's vital from the data science and AI perspective is that if we can leverage artificial intelligence and data science and automate something which can be automated, reduce the human errors, improve the administration work with the help of predictive models and the health outcomes, improve the health outcomes using the latest AI and data science approaches, it will result in cost reducing, at the same time not compromising on the value. So this, after even though the cost is still going on, but the whole purpose of building this necessity of electronic health records was to to reduce the human errors, because this is a 1999 research which provided the information that there are many preventable deaths. People are dying because of the human errors which can be prevented in the healthcare. And then also high cost associated with it. And this led to the further development of EHR. And then we heard about President Obama Healthcare Act, which talk about meaningful use stages, which was data capture and sharing, advanced clinical process, improved outcomes, and overall the whole spectrum was that it will improve the quality of patient care. But while if you still see we are not there in terms of advanced clinical processes and data capture and sharing, even if you move from one state to another state, and if you want your healthcare data to be shared among different providers, you still feel a lot of back and forth, and sometimes even you end up getting your healthcare record faxed, and it's not being electronically shared. So there is still a lot of work to be done in interoperability and how the have different healthcare sectors and hospitals especially, how they can share them and exchange the patient information. So there are some work is being done from the meaningful use, but there's still a lot of work which is desirable to improve the outcome. So this is a brief overview of the healthcare, where we are and the kind of opportunities we have to leverage data science and AI to improve the outcomes and to streamline a lot of processes to reduce the administrative cost and improve the workflow, at the same time improving the value for money in terms of per capita spending. And now we come to the structured data and unstructured data. Structured data, what is structured data? If you talk about structured data is well organized in the tabular format, everything is very clear. If you look at the left side, this is very well organized. And unstructured data is difficult to organize. It's mostly the narrative text. And then if you can include audio files and images, they are also classified as unstructured data. And if we look at the trends right now in the modern era of social media, internet, we are creating so much data there, and most of the data is unstructured. Even if you go to in the healthcare perspective, in the bedside, we are using so much machines which are constantly generating signals, audio, video, so textual data. So all of these data is unstructured format. So there is a lot of data. Even if you can say going forward, 95% of the data will be unstructured data. So we have to find the way to leverage that unstructured data to convert into a meaningful information so that we can utilize various downstream data tasks. So now we come to what is natural language processing. So natural language processing basically is needed to extract the value from the unstructured text. So healthcare industry needs a new needs technology advancement to maintain value-based care for every patient. NLP can help us to transform this raw data into meaningful insights to improve healthcare outcomes. NLP can be broadly described as the process of we can identify information which we are looking for. To give you an example, let's say want to know what drugs are and what their adverse events are in the research paper or in the article. So it NLP can come in and extract as the which we call named entity extraction. So but even this data is there, but language is irregular and ambiguous. What I mean by language is any spoken language. If we speak English, French, Spanish, all these languages are irregular and ambiguous. What I mean to say here is that different words have different meaning in different contexts. We will see some examples down the line, but this is talking about, and language is constantly evolving. For example, if you go back 5-10 years back, you will not find a word Googling. Now if we are looking for some word, everybody say, oh, Google it. You can Google it. So Googling is already being added as a term which we use to search. And these were, so language is constantly evolving. New words are keep coming in the language and being adopted from different languages also. So language is irregular and ambiguous. And because it's irregular and ambiguous, we need a different level. Understanding the language involves processing at various levels. What are those levels? Morphological, structure of words, how the words are being formed. Syntactic, what is the structure of sentences? What I mean by syntactic is what is the verb, what is the object, and similarly, so what is the subject? Semantic, what is the meaning of words and sentences? So what they mean actually semantically. Discourse, pragmatic, interpretation of utterances in different contexts. So let me explain a bit more in detail what I said here, morphological or lexical. So morphological or lexical is lexical ambiguity is ambiguity among words. If I say discharge, now discharge means this is the two usage which are totally different, and both are right in their own domain. This patient was prescribed codeine upon discharge. So patient was given a medicine after he discharged from the hospital. The discharge was yellow and purulent. If you see both are coming from the medical domain, healthcare domain, but in both places discharge has totally different meanings. So that's an example of lexical ambiguity or morphologically how the word is being formed. Syntactic ambiguity. John saw the man with the telescope. Now, if so, here the ambiguity is if John is watching the man, seeing the man with the telescope, or John is seeing a person who is holding a telescope. So that is syntactic ambiguity. You need to have more context to resolve this. The who is the person who is holding the telescope. John saw the man in the park with the telescope. So if John is using telescope, or the man who he is seeing is holding the telescope. Then we come to the next phase. So these are all like for if you in the pipeline, these are all steps which you have to do in a certain level to about your various use cases. So semantic ambiguity. The rabbit is ready for lunch. Is it mean this, or is it mean rabbit is cooked and ready for lunch? So there are totally different semantic meaning of a given sentence until you know the context. Then we come to the anaphoric ambiguity. What mean anaphoric is that we use a lot of us we use pronouns. So for us as a human, when we speak, we can refer that this pronoun is referring to which entity. But for computer, we have to provide this information. Just to give you an example, John put the vase on the plate and broke it. Here it is referring to vase which is broken. But if we are using machine or computer to process it, we have to provide that kind of information that what it means it here. Is it referring to plate, vase, or John? So that's include another layer of ambiguity which we have to resolve. The soldier shot at the woman and they fell. Who fell? Here, woman. So these kind of ambiguities, anaphoric ambiguity, where pronouns are referring to which entity, these are also itself in whole field area where anaphoric ambiguity, there a lot of work is being done. Then interpretation, pragmatic. You owe me $20. Is it effect, or am I requesting the money from you? So all of these examples, they add different level of complexity as we move down the pipeline. And that's why it's very well known in linguistics that context is very important. You shall know a word by the company it keeps. And that is also, context is so important. Like, for example, we see the context in terms of major breakthrough comes in NLP when the word to vec came. And that was where when we use embedding concept, we use embedding. So, but there was some work being done, but the major revolution in recent history came when this 2017-18 time, when the BERT came. BERT is a big language models, what the language models comes. So what they did is language models have context, they provide context, but with the semantic information. What I mean to say is that if you are using word to vec or glove embedding, and if I say the person is walking on the river bank, and the person goes to the bank to withdraw the money. If you are using word to vec or glove or earlier embedding, that are non-contextual embedding. So you will get the same textual numeric representation or vector for both words bank. They will be same representation because they don't have the contextual information. Since the language models such as BERT, XLNet, Universal Sentence Encoder, these start coming in 2017 to onward, the major revolution is NLP is happening because then the word bank will have different meanings in different contexts. So they bring a lot of information. That's why it has revolutionized the whole field, and there are a lot of research is coming up and a lot of work is being done in NLP domain also in terms of dialogue, chatbots. You see a lot of those kind of work, which was basically based on a lot of work are using language models. So now we talk about natural language processing, an opportunity to realize the vision of EHR. So and now we'll talk about a specific use case that was being built with the collaboration with the cardiovascular physicians at Mayo Clinic. And after a lot of validation, improvement, and back and forth, this work is currently being used real time at Mayo Clinic. We will talk about that at the end also and what it is. So there is a cardiovascular disease which is called peripheral arterial disease, or PAD in short. So what it is? These are 2016 figures, so the numbers will definitely be latest. I don't have the latest number, but it will be much more than that. In 2016, it was reported that it affects 8.5 million people in US and 200 million people worldwide. It has high morbidity, but often undiagnosed and undertreated. We'll talk about why. There is a lack of physician and public awareness of PAD-associated risk for adverse cardiovascular outcomes. So that's the disease. Why it's a problematic? The problem here is one, first of all, there is no single ICD is international classification of disease. They provide a diagnosis code. So there is no single diagnosis code, either ICD-10 or ICD-11 for that. Second thing is it happens after the people after the age of 40. And a lot of time it goes undiagnosed because they may have other health complications. And by the time it's being detected, it's already too late. Too late means is it severely affects the person mobility. So it happens from the belly button to lower limbs. And most of the times, if it detected so late that it results in either amputation or death. So in 2008, it was reported that 4.37 billion spent on PAD related treatment, and 88% of these expenditures for inpatient care. So if we facilitate earlier detection, surveillance, it can reduce the cost, it can improve the quality of life, and it also saves human life, or at least maintain it, because this disease is not cured 100%, but it can be maintained following the NIH, National Institute National Institute of Health recommended guidelines for this disease, associated disease. So what it happened is that how it's being diagnosed in current setting is that they measure the blood flow at various parts of your lower limbs. So in resting position, and also they have the treadmill, or they ask the people to walk quickly and then they monitor again. So at the rest and the post exercise, they measure the blood flow at different places on your knees, on your ankles. And if they found that the blood flow is that is called ankle brachial index. So they have the guidelines, healthcare guidelines, which they see what the blood flow look like. And if you have a less than those scores, then they say that you have this problem of PAD. And most of the time, these are not available in EHR setting. In Mayo Clinic, these were stored separately in PDF format. So sometimes doctors, if they are seeing the patient journey, they review the healthcare record, they don't have that information available in EHR unless it's being what you can say, it is being specifically typed in by the physician or being dictated by the physician. Sometimes they forget, and sometimes they even are not aware of that it's being somewhere because they don't have time to go through all the previous patient history sometimes. So that's another problem of late detection or undetection. So there is no automated process for identification of PAD patient from narrative clinical notes. Use of NLP to extract PAD related information from narrative clinical notes. So now the question comes is how currently they recognize before this NLP approach. So before that, the same cardiovascular physician team, they have already developed certain ICD code and CPT code. CPTs are different procedural codes. So CPT means if somebody is go through angioplasty, that there is a specific classification code for that. That is called CPT code. And then there is ICD codes. So what they find was previously, they find out that if the patient has these list of 7 to 8 specific codes, ICD-9 codes, then we say that this patient has PAD. And then they built another model which say that if these procedural codes plus these 8 codes, these both are present, then the patient is PAD because there is no specific code for that disease. So the same team wanted to build a better way to approach to detect this disease and say that they develop NLP algorithm that ascertain PAD cases from clinical notes in EHR and outperform those previous approaches. And plus it also has a way for a physician to track back. So they want to be hold this approach driven by themselves. It's called a data-driven approach. So they don't want it to rely on machine learning because it may be result in a prediction which were not highly accurate. And they don't want to be sued in terms of physicians. So they wanted to know how the whole process of detection is being performed. So what we did was we work with the team of cardiovascular physicians that if you have time, how you find out that this patient has PAD if you only have access to clinical notes. So working with those teams, we find out what kind of this, look for a specific disease keywords, and then with a specific location. And if they are happening, so we build these kind of rules working with them, like PAD criteria, what it is, what they do in normal procedures if they have the time. So from working with them, we build this kind of, this is one picture, but we have 5 or 6 different diagnostic terms and 5 or 6 different sets of locations. And then similarly, we have different exclusion keywords. Here I want to also point out that PAD or peripheral arterial disease is very closely related to aneurysm, which aneurysm happen upper parts of the body, and the PAD happen lower parts of the body. So there is a lot of confusion there also. So we have to work that if a certain location is mentioned with the diagnostic term within a certain time frame window, then it's a PAD case. So we work back and forth with the team of cardiovascular physicians, build those kind of rules, validated those one, made the changes according to that. So in this way, we have 5 or 6 different sets of location terms, 5, 6 different sets of diagnosis terms, and then separate exclusion criteria, and then different combinations if they are happening in the text within a clinical notes in a certain what you can say sentence window, then that will be a PAD case, and if not, then there will be control. If they are exclusion word, that will be a control. So this is the kind of the whole EHR system. So this is the whole process is reported in this Journal of Vascular Surgery. So we use an open source tool, which you can use also. It's a Apache open source based on Java UMF framework. It is called MedTagger, which is freely available, which was built by Mayo Clinic. It's based on Java UMF framework. So, and then we added these further work information. Like, let me just explain this. So we did the NLP algorithms take sentence detection, tokenization, concept identifications are the terms which we are looking for. Assertion means if those diagnostic terms are mentioned positively, negatively, or probably. So our positive cases were those where this information is mentioned positively, there is no probable, and they are no negated. And then we have sets of rules which classify the patient as a case of control. Then we have the simple model, which was previously, as I said, they have 8 ICD-9 codes. The full model is basically ICD-9 code plus procedural code. And then we have some data which we wanted to look for surveillance. This is the gold standard data. So ABI gold standard data, which we are comparing these results to, and in the final evaluation phase. So let me explain a bit further here. So me just so this is a kind of a window of the tool which we are saying this is a, if you see on the right side you see a part of a clinical note, and if you see on the left side, if you see left bottom, you see here that this we have identified arterial occlusive disease in the clinical note, and if you see here we say match which category of diagnostic terms it belong to. It belong to first diagnostic occlusion. And then if it mentioned how it's mentioned, it is mentioned positively. There is no negation there. So who is the experiencer? It's talking about patient. And then the next phase, what we did also, the next what we do is we look for our location terms. We say we detect lower extremity, and these are within a 2 sentence. So lower extremity. So this belongs to one of our category, which is location 3, where we have the rule that if first diagnostic occlusion comes with the location 3, and if it mentioned positively experiences patient, that is a PAD case. So this we are these are some examples. So when we say that this is a patient of a PAD, when we produce the output result, it will contain that snippet of a text note for a physician to look how the system is being deciding. So the final output will have these small snippet of text and with the patient ID and date and every information that based on these ones, this is the case here. So the physician can go back and validate in clinical notes also to make sure that the system has made the right decision. So we use a Rochester epidemiology project. Basically, that is in Rochester, then in the Minnesota Olmsted County, they have all the information about the patient who from who was born there, and then some of people died there. They have the whole history of those one. So that's a big cohort. So from those cohort, we physicians selected 1,569 people, which we have all the patient history, and out of which 806 was cases and 763 were control. So we split those cohorts into training and test data set. In the training data set, we built a system we take it out to the cardiovascular team. Our result, they validated if their recommendations were incorporated again in the false positive and false negative cases. And once that is done, then it was finally tested on the unseen test data set. And if you and then also in here we also find out that because Mayo Clinic men have the electronic health record of 1998 onwards, so some patient has a very, very long history, and some of the notes were not relevant. To improve the prediction time also and the processing time also, we work again with the physician to see which notes are vital or related to those this PAD. So we included only those note types, note section, and service groups. Service groups are specialty, means cardiology, vascular, pulmonary, because we have seen that a lot of people, like for example, uh, it has nothing to do with podiatry, dietitian. So we take or even the dermatology department. So we take out all those departments to improve the workflow and the processing time of those notes and also the data. So these are the information like consultant notes, subsequent visits, these kind of information we kept, and then we exclude, these are the which were not relevant, we excluded those notes. For example, it has nothing to do with allergy, dermatology, spine center, plastic surgery. So we excluded. If the note is coming from these departments or physicians from belonging to these service groups, we just excluded those ones and during our processing time. So then on a testing data set, we compare in terms of sensitivity, specificity, positive predictive value, negative predictive value, and accuracy. We compare them, and we found that there is statistical significance difference, that the NLP model is performing well in terms of specificity, positive predictive value, and accuracy. And these results were reported in Journal of Vascular Surgery. So once we have these information validated, and in terms of accuracy, and we see that it's outperforming the previous approaches, then the next phase was also to look at all those positive and false negative which we got. So why we are getting those ones? So we further analyze those one with the cardiovascular physicians, and we find out that some cases were probable cases, suspected PAD, but our system was not able to. Our system was saying NLP system is not 100% correct, so it was saying that these are the patient is the PAD, but they are suspected PAD. So these are gray areas. Even the physicians have to discuss among themselves to say, okay, this is a real case or not. And then we also find out how the notes are being written, and also how are being dictated. For example, here she lives with her husband, who is a status quo. So suddenly the note turned from her to her husband, and her husband has the problem of these PAD, not her. So, and but the language is in such a way it changed the context for us. The system was unable to mitigate those one, but there are very one case we have that kind of example here, where it's suddenly the context changes from the patient to the partner. And we also look at what happened other cases also in terms of false negatives. So she clearly has peripheral arterial disease, but the left is worse than the right. Now, for a physician, it's very clear that this is PAD. The left is worse than the right. It means it's talking about the left limb is worse than the right limb. But when the physician wrote the note, he or she forget to write limbs or lower extremity. So as NLP system, we don't find that word and we say this is not the case. So that is how the language is being dictated or written. Then also we find some of the typographical errors also. But these errors are less, because if the patient has PAD, it will be mentioned maybe multiple times in their clinical history if the diagnosis. This ABI, it should be ABI. Instead of ABI, it's written as ADI, and we missed that example there. So summary of the clinical, this resulted that its approach is performing well, highly accurate, and it can facilitate the physicians. It is improved accuracy is better compared to billing code or ICD-9 algorithms. It can support the big data for translation to patient care. So once that was validated, this this phenotype or this methodology become a part of a bigger consortium. So then the next question was, is it work in different EHR setting? Because different organizations have different EHR settings. So then it part of a become a NIH funded bigger consortium, and that was validated on the two different sites, which was Columbia University and Vanderbilt University. So there we have the physicians, cardiovascular physicians have to work with their cardiovascular physicians, and our side, AI and data science guys, we have to work with their implementation on the data scientist to implement that system. Because, for example, in some EHR setting, they said discharge summary. When the person is discharged, they called it labeled discharge summary. While in some, they said dismissal summary. So it's the same word, but different terminology. So how we align those one? So we work with those cardiovascular teams, and we made the changes according to the note types and notes, and they validated it, and they found it that it is working well. So they validated on their EHR setting, and that algorithms was performing really well on both our Vanderbilt and Columbia University medical centers. So then it comes to this is about the data. As I said, that the most patient are after 40. So average age was 71 years, 44%. And because the Olmsted County or Minnesota is predominantly based on Caucasian descent, so we have most of the population was 90% white. So we wanted to report that one also, because that's what data we got. And next phase was that, okay, can we do it if we want to use the same algorithm for surveillance purposes? Because many times what happened is that ABI test is done, and when the patient comes 21 days after to see his physician, his or her physician, and they generally talk about that report. But can we do before this ABI test date, can we process all the notes and detect earlier and send an alert back to the physician or something? We can build a surveillance system which can detect earlier rather than the patient reporting based on the conditions which are being dictated in narrative notes for surveillance purposes. So in order to do that, what we did was that we took a data set, and about 806 cases only. We took only the cases data, and we see we already know when they were detected PAD, like when it was actually reported that they have PAD. So before that date, can we detect looking at the clinical history? Because most of the time physician does not have to go through the time to go through all the clinical notes. So we find out that we were able to detect 41% of the cases earlier using our algorithm and trying to find out before that date. 93 cases, 12% was those where we were able to find the same date. And some of them, because they were reported once they seen the physician after their test, so we found 18% was there. So this resulted, and some of the cases we were able to find much earlier, a few years earlier, especially in the cases where the patient has a huge history. They are being living resident of Minnesota. They are coming to Mayo Clinic through all their life, and they have grown old, like 70 plus, and they have the whole history of that. And if we can process those notes, some cases we find out 500 days earlier than the patient was actually diagnosed by by ABI test. So if we can detect earlier and send an alert back to the physician, it will improve their quality of life, reduce the cost, and also improve the health outcomes. So after this kind of study that was published in AMIA AMIA American Medical Informatics Association conference, these results. So after this, we work with the Mayo Clinic data architecture, big engineering teams and IT team. And basically that's happened is that when the EHR system, when the physician goes to the patient, see the patient, but they either dictate or type in the notes in the EHR system. That goes in the terms of a messaging system into the system. So what we did was we built an NLP system with the software, with the help of IT team, that as soon as they receive that stream, and if it's coming from the predefined healthcare department which we are interested in, specialty, like if they are coming from cardiology, if they are coming from pulmonary, or that's our relevant field, it will pass through that NLP system. It extracts that information, and if the patient is showing the symptoms, if the system says that this is PAD case based on this clinical note, it will send an alert back to the physician saying that this patient is showing this PAD based on this note. Can you order the ABI test so that it can be detected earlier? So that is currently being used at real time, where um, as soon as the note comes from the specialty, this algorithm runs on top of it, and if it's detect that the patient has the symptoms of PAD, it can send an alert back to the physician that based on this note description, it provide an evidence like a 2-sentence window that based on this, the system is saying that this patient is showing the symptoms of PAD or PAD. Can you please order the ABI test to validate it and then take the NIH guidelines to maintain that patient health. And these are the various related publications which were comes out. All the top ones in the below are the various journal publications which are related to that. And one thing I forgot to mention here also, that we also did a survey with the physician, which on a beta version or alpha version, where we asked that physician that do you need to find this system useful, and that was also reported here in terms of American Medical Heart innovation and quality and outcomes, that if it will this system you find useful, it will improve the health care outcomes, yes or no. And we did a lot of surveys there also. So based on these kind of information, we adopt change, and these are the and then this is another part of critical limb ischemia. Similarly, critical limb ischemia is a subphenotype of PAD. What I mean to say is that if the patient has PAD, it may have critical limb ischemia, but if it does not have PAD, it will not have critical limb ischemia. So, and there is also no ICD-9 or ICD-10 or ICD-11 code for critical limb ischemia also. So we develop another approach with the subphenotype, which comes to identify critical limb ischemia cases also. And I will finish with this, that the wisdom is not the product of schooling, but the lifelong attempt to acquire it. From Einstein quote, that still this is just the tip of the iceberg. There's a lot of things to learn and improve. There are a lot of other phenotypes. There are a lot of other use cases where we can leverage this narrative unstructured data. Even there's a lot of, I know there's a lot of already existing work which are working on EMR and images, MRI scans, those kind of work, but there is still a lot of scope to work in terms of textual data also and drive value for various use cases. Thank you. And if you have any questions, I'm ready for those.
Yes, please. If you have a question, you can type or you can share your, you can open your mic and ask.
Assalamualaikum, sir.
Welcome. Go ahead, please.
सर मैं मोहम्मद इमरान खान बात कर रहा हूँ पाकिस्तान से। सर आपने अभी बात की है कि OMR और OCR के थ्रू
we have international audience, so if you can please talk in English, that would be helpful to us.
Okay, I can talk in English. Sir, myself Mohammed Imran Khan, I am from Pakistan. You already discussed earlier about the OCR and OMR solutions. Here in Pakistan, I am facing a problem related to OCR. I have an image of a restaurant receipt, and I want to convert that receipt data into a CSV file. There is any facility, there is any software related to this problem that can convert from image data to a CSV file or Excel file.
So there are a lot of existing packages, a lot of research which works on OCR data and which work on there's the whole other domain of research and area which work on specifically OCR data, and also how to transcribe OCR data in terms of extract value. Because so there are a lot of healthcare departments receive information in terms of faxes. Faxes are mostly OCR. So there are a lot of work being done from OCR, which is basically a picture. So how we can extract the text data from OCR. So I haven't worked with the computer vision side of things, so I don't know about that, but I know that people are using those faxes OCR images, and they are converting those OCR images to text and extracting value from it.
Sir, can I have a resource person or any researcher who is working on this problem? Can I have the LinkedIn contact or any other
And
contact detail?
you can
I
send
want to discuss that problem with the.
Imran. You can send email later on. We just want to give time for the other participant to ask. You can send email, and then we can communicate later on. Thank you.
Okay, thank you.
Yes, please. If you have any question in audience, please go ahead. You can ask through your mic or you can type.
Hi, my name is Steve. From what you were saying earlier, in terms of how you were able to, I guess, test the algorithm I guess, on various people with their medical histories. I guess one thing I was wondering is how were you able to, I guess, put together in a standardized manner the different patient histories, because I would imagine that their visits may be for different things. So how are you able to kind of I guess standardize that medical history to feed it to the algorithm?
So we took all the data. So for example, if the patient is belong to our control, what we see is uh, either case or control. We see that the patient maybe comes in Mayo in 2000 and up till 2015 he's visiting, and they are different notes. So we took all the information first, and then once we filter out all the information which are coming from different departments, because generally the notes, there is information there that which department the patient visited, the which note is coming from. So we filter out those which were not relevant to our healthcare department or specialty, but we kept all the data. And then, so that's why I'm saying that we have millions of in terms of notes to process. So millions of notes were processed by the NLP algorithm. So that's why one of the reason was to filter out the relevant and irrelevant department to improve the workflow, because it took quite a bit time to process all those, extract those informations, analyze those one. And also at the same time, we said that if we found the evidence, as soon as we found the evidence, we will have the date there. So it produces an Excel sheet as an output, which we say that this patient, it found this evidence on this date. So we find out earlier possible evidence on the when all the conditions are being met. So in this way, and then once that Excel sheet was produced, that was taken back to the cardiovascular team. So that was analyzed. So this is our result for this patient. Our system is producing that this patient is PAD based on this note, and this is the window. So if they have any doubt, they can debate in the cardiovascular team, or they go open up their EHR system and to double cross check it. So basically the whole purpose of filtering out the specialty and non-specialty was to ease out the burden, because we were processing millions of nodes. Some people have history from 2000 to 2015, and they have, as I said, they were mostly over 40 years old, so they have a lot of other health complications. They may come from diabetes, and may come from cardiovascular surgery or something. They may have other health issues. So we basically process all the notes and look for our specific information which we are interested for this phenotype.
Okay, gotcha. Thank you. That made a lot of sense.
Very nice. Well explained. Any other question?
Can I ask the questions?
Yes, sure. Please go ahead.
Yeah, let me first introduce myself. I am Dr. Naveed, a Fulbright scholar in St. John's University. Dr. Naveed Afzal, thank you for a nice presentation. It was a great and beneficial talk, so thank you for that. So my question is related, as you mentioned earlier, regarding different ambiguities related in unstructured data, especially for when you apply different natural language processing techniques, like we have semantics, So one sentence does have a different ambiguity. When you do the tokenizations and finding the keywords, so the some keywords will be same for one disease, right? And there will be some keywords that will be shows the ambiguities. So how you resolve that issue with the keywords which have an ambiguities for the different disease?
So we use NEGEX algorithm. NEGEX is a algorithm. If you so we have used UMLS to identify different procedures. So if you download this MedTagger tag, that is a, I'm not familiar, maybe audience have heard the name CTAC. CTAC was one of the bigger tool which was released by Mayo Clinic and Apache. And then MedTagger is a scaled down version. So there we have a, for assertion, we have the NEGEX algorithm. So NEGEX algorithm is to tell you that your specific entity is mentioned positively, negatively, or probably. And then also, as I said, we are looking for a location term and the disease term. So it may happen that diagnostic term is mentioned, but with different locations. So if that's the case, if it doesn't fit in our criteria, we will exclude those ones. And also we had the NEGEX algorithm, and then we further modified it. For this specific cases, I added more rules into it. So this is, if you, there's a lot of literature is available for NEGEX algorithm, which is basically used for assertion purposes. So that was used, and we even modified it to improve it in our, for our use case.
Okay, thank you for the answer.
Any other question? We still have time. We have up to 6 minutes. So if you guys have any related question, you can ask.
Hi, this is Giancarlo. How are you?
I'm good. Thanks for joining.
Yes, very good presentation, very interesting results. As a disclaimer, besides teaching at St. John's, I also work for a pharmaceutical company. So same domain, even though from different perspective. Mine is more a curiosity. You rightly mentioned at the very beginning the success of embeddings, especially now the contextual embeddings. And I was wondering, but you decided to go into a more rule-based system. And I was wondering if this was for a practicality issue or there was something more.
So there are two aspects, even though I built a machine learning model for that also, but the problem was that they wanted to have all the matrices like specificity and everything in 90 plus. And they wanted to have, if we use embeddings and then we use deep learning or something, sometime it become a very complex kind of black box. So they wanted to, one highly accurate system with machine learning with so much rules and with the specific information, we were not able to achieve that kind of high level of precision and accuracy, one thing. Second thing is they wanted to have a better solution which outperformed their existing one. The existing was already like 70% correct. So they wanted to have something which is in 90s. That's one reason. Second thing is when you are putting something which is being used at real time in a practical setting, so then the doctors and physicians, they are very reluctant. They don't want to have a black box kind of solution sitting there doing this disease detection kind of role, which they find it very reluctant, but because there are a lot of chances that they can get sued. But coming to that side, we have already in another paper, if you follow my Google Scholar, we are already used, we build our own embedding for internal use at Mayo Clinic for research purposes, where we take all these clinical notes data, not for this use case, all the clinical data which is available at Mayo Clinic. We build a clinical embedding, and that was used at real time for various downstream research tasks, not in a like a practical system task. And also a part of that, we also did a semantic similarity shared task, which was that we have some data which we build from those clinical notes, and you are given two sentences and you have to build a semantic textual similarity system that based on those clinical data, it says how similar those two sentences are, how from 1 to 5. There are a lot of those semantic similarity shared tasks being held by the different ACL conferences, but there was no clinical data which is coming from the real. So we build that one also. So we use those embeddings and other tasks for various downstream research tasks. But when if the system is going to be in practical setting, unless we have a very clear machine learning algorithm which they can track down, like for example, if you have a decision tree or a random forest where they can actually see how the decision is being made, or even logistic regression. But if the models are very complicated, then in the real setting, they're still a bit reluctant to see, unless you have the human at the end of the loop. Look, for example, what I mean by human end of the loop is that there are a lot of MRI scans which are being passed through the algorithm, and algorithm says that if they detect any kind of abnormality, it says that, and that is then further post-edit human validated. If that kind of setting, yes, but this one, they wanted to have the better solution compared to what they have already. And the second is how the decision is being made. So the systems, in this, we are providing them the evidence which based on which note it's saying that.
Thank you so much. Just a quick follow-up. What was the acceptance of such a system from practitioners?
Yes, so let me, that was very interesting. So what we did was, let me just point to you if you are more. So in this one, we did a work here, innovative informatic approaches for peripheral arterial disease, provider survey. So we did a survey first for those physicians and asked them that what they found PAD, what are their problems, and if we provide such a system with this facility, would you like it or not? So we first conducted that surveys to improving the guideline-based cover specific to that disease. Once, and then we took that survey in, and then once we have the build the system, we said, can you use that system to what you feel? So actually there was in EHR setting, we have with the IT team, we had a whole page which can, for this was added into it so that they can improve the workflows and everything. So this was like they did some, before we seek their information from the form of surveys, and once we build the system, they were asked to validate it, to use it. They find it handy what they are, because sometimes even the physicians were saying that we don't want too many clicks. So when we put this one into production in the EHR setting, we try to minimize the number of clicks they have to do to look at the algorithm output or alert. So how the alert being designed, how many number of clicks they will have to view it, and how. So for example, if the system send an alert back to the physician that this patient is showing the symptoms, they will have a note information to window. So they just need to have clicked that note, and whole note will be open up in a pop-up window. So they can, very few clicks, they can review it, why the system is saying that this patient has PAD.
Very nice, very nice. Thank you so much. It was so insightful. I learned a lot and enjoyed a lot. I mean, for me, the biggest lesson I think which I could remember, I definitely have to once again watch the entire video. We shall know a word by the company it keeps. The context is everything. Well, thank you so much again, and on behalf of our healthcare informatics program, our division of computer science, and on our college, CCPS, and on behalf of our university, we are all very, very thankful for sparing time and sharing your knowledge, experience with our faculty and students. And we will try to invite you in future, hope so, for our next room.
Sure.
Thanks.
Thank you very much. And just to add here that one of your colleagues mentioned pharmaceutical company. So in one of my role, I built a pharmaceutical healthcare predictive system also, which was basically if the research is talking about adverse event or not, and that was put into production and commercialized when I was working with the Wolters Kluwer previously in my previous role. So hopefully in the future we will talk about that one.
Perfect.
Thank you very much.
Looking forward to that. Thank you. Bye.
Thank
Bye.
you. Bye.
Thanks, everyone. Thanks for joining.